Hi, everyone. Can you see my slides?
Yep, but not slideshow yet.
Yes. Let me see how to... Oh, there's the play button. It was hiding. Okay, there we go. I seem to have lost my mouse now, too. There it is. So hi, thanks for giving us this opportunity to present our recent work on NAMD. So NAMD is a scalable molecular dynamics code. It is one of the earliest Charm++ applications, so the code is written in C++ and Charm++ and CUDA. And our performance scales to hundreds of thousands of CPU cores and tens of thousands of GPUs. And we can really scale NAMD simulations in a couple of different ways. One way is to take a large system and do like this single copy strong scaling of the system across multiple nodes. And then another way is to employ some sort of enhanced sampling technique with multiple copy scaling. And so in this case, you might have a much more modestly sized system. And then say you've got one copy of your system per, say, GPU on your parallel computer. And then you could do multiple copy scaling across all of the GPUs in the computer. And so anyway, and we're interested in supporting both of these approaches because both of these are important for scientific investigation. So NAMD runs on laptops up to supercomputers. We run on the AWS cloud and MS Azure. We also provide something that distinguishes NAMD from other MD codes. We actually provide a TCL scripting interface. And so this can actually provide a form of workflow control or even some sort of higher level method development. And we do structure preparation and analysis with VMD. And in particular, we have a plugin now to VMD called QuickMD that gives scientists a really accessible interface to NAMD for setting up their simulations and getting themselves going. So some of the highlights of NAMD are these advanced features that we provide. So we provide a collection of user-defined forces. We provide these accelerated sampling methods. So one in particular that I'll mention again is replica exchange, in which you're running a number of these small systems, and then
David, I think you're not progressing off the title slide for our view.
I'm not. Okay.
We need to break out of the play and restart it or something.
Aha. Stop sharing. Let's try it again. That'd be a shame because I have some really nice movies in there too. So. Can you see that?
Gray screen right now.
Sorry, what is it that you're seeing? Or not seeing?
Displaying gray screen.
Just a gray screen.
Yeah, I got the same thing, gray screen.
Huh. Do I need to maybe exit from Zoom and rejoin Zoom? Will that help? Or is it just an issue with playing a slideshow and for some reason it doesn't share the screen correctly?
Not sure.
Any suggestions?
So Dave, which option did you choose when you try to screen share? Are you sharing the whole screen or just the application?
Just the application.
Okay. Could you try doing the whole screen instead? See if that works.
Yeah, okay. Let's try that instead. So let's share the desktop. How's that?
Okay, and move forward and back one slide just to make sure.
Okay,
Yep.
Yeah, seems to work.
You're good.
right. So this is one of the slides you missed. Sorry about that.
It's beautiful pictures too. We don't want to miss them.
Right, exactly. So yeah. So the movies that hopefully you now are seeing are illustrations of some of these advanced features that I'm talking about. So the user-defined forces with this proteasome simulation, the use of grid forces to do this membrane vesicle fusion and formation. So another important method in NAMD is this collective variables module. And so this is actually a separately developed a library that we include in NAMD. And so we don't develop it ourselves, but we work closely with the developers of Colvars. But this allows a lot of flexibility in how you could define collective variables that you could use to bias your simulation and enhance your sampling. So for instance, this ABC transporter mechanism, the collective variable had to do with defining sort of an angle and then forcing that, transporter opened and closed. We have a rich collection of alchemical transformations. These allow us to do free energy perturbation and thermodynamic integration. And we also can attach NAMD to do hybrid QMMM simulations to various QM packages as well. So when we're doing molecular dynamics simulation, at its most fundamental level, we're integrating Newton's equations of motion. And so this is just a system of ODEs that we're integrating in time, but up to billions of time steps. And most of the computational work is in calculating the forces between atoms. And in fact, the most expensive part of that are the non-bonded forces that are due to Lennard-Jones and electrostatics. And so the parallelism for MD simulation is limited then to each time step. And so if you just look at the computational workflow, you'll initialize, say, particle positions, and you will calculate forces on those particles, and then you'll use those forces to update the positions again. And you'll sit in this loop for millions or even billions of time steps. Occasionally, you will do some output to supply some reduced quantities to the user, like the energies or temperature or pressure, or even less frequently, you might do an entire snapshot of the positions to record what your trajectory has been for this simulation that you've done. And so the force calculation itself, that's somewhere in the neighborhood of 99% of the computational work. The updated positions is much smaller. So a lot of work has gone into NAMD to decompose these force terms into these fine-grained objects that then we can schedule and move around, load balance for scalability. And so when we've applied GPUs to do this calculation, we've offloaded forces to the GPU. Now, back when GPUs were less capable, we focused solely on the non-bonded forces. Today, we load almost all of the forces to GPU. And so this strategy has given us a lot of scalable parallelism. And so here I'm showing you some of the scalable results where we're measuring performance in terms of the nanoseconds of, or the computed nanoseconds of simulation per day, and then shown, on the number of nodes to achieve that performance. And so these are strong scaling plots here on two of the leading supercomputers right now. And this case is showing just our synthetic benchmarks that are created by replicating this STMV million atom virus and tiling space with it, so that we can create whatever sized benchmark seems appropriate. The two that we have generally been using are this 224 million atom matrix and this 21 million atom matrix. Well, recently we've had the opportunity to work with the Amaro lab at UCSD, where they've been simulating the SARS-CoV-2 on Summit. And so so these are some really nice results here, where they've done this scaling performance of this 305 million atom virion, and then we went ahead and scaled it across almost all of the nodes available on Summit, and what we saw is that we got reasonably good, strong scaling efficiency for this application, MD, so it continued to be about 50% efficient at, the ends of, what the resources that Summit provides. However, when we have done benchmarks on single nodes or newer GPUs, it's revealed problems. And so we can take a look at, say, the NAMD 213 performance going from Pascal to Volta, and we saw a 20% performance improvement just when we're running our standard 8x1 benchmark on just a single GPU. However, the hardware itself had a 70% performance improvement. So we haven't been taking full advantage of the GPU. And we can see that when we do some profiling on these modern GPUs. So this is something that was produced by Insight Systems, where you can see these gaps in the blue strips here on the plot. And so that's showing where the GPU is idle, where we're not keeping the GPU busy. And so the problem is that, NAMD 213 and now NAMD 214 have limited GPU performance. And the issue is that offloading force calculation is not enough. Our overall utilization of modern GPUs is limited now by the CPU work. And it's limited by that, 1%, amount of work that I showed that's just due to the time stepping that is still on the CPU. So we want better single GPU performance, also because the majority of MD users are running system sizes that are less than 1 million atoms, which works really well on a single GPU. So what this means for us is that we must transition from a GPU offload approach to a GPU resident one, in which we are maintaining data on the GPU across time steps. So we've been working now on developing this over the past couple of years on developing a GPU resident version of NAMD. So in this case, we are fetching the GPU force buffers directly from the force modules, we're bypassing any of the CPU, GPU memory transfers so that we're only calling the GPU kernels. And we've also converted the forces into a structure of arrays, data structure, and this way we can invoke the GPU integration tasks once and do that on the GPU and keep all of this data on the GPU. And so this development has led to better GPU utilization. And so now if we compare to the NAMD 214 profiling, where we see the gaps between the GPU tasks, NAMD 3, we don't see these gaps anymore. We don't have the same CPU bottlenecks that we used to have. And so if we look at what the overall performance is now on different systems, we see that we can get really good performance on small systems like the Jack benchmark from the Amber community that we used to not really perform well at all. And so all across here, we're seeing a better than 2x performance improvement now on when we more fully utilize the GPU. And furthermore, by pulling all of this work off of the CPU, it allows us to get really good aggregate throughput on hardware that is GPU dense hardware, like a DGX2. And so if you're looking at the DGX2, you only have 48 CPU cores there, so you only have 3 CPU cores per GPU. For the older NAMD 214 or earlier, it really required a lot of CPU power to be able to do this calculation and for the CPU to try and keep up with the GPU and feed the GPU. Well, now we can run these benchmarks perfectly well just on 1 or 2 cores per GPU. And really what's getting all of the work now are the GPU. And it allows us to just fully saturate a dense GPU dense system like this with work. And so that's what we're seeing here when we're calculating now the aggregate throughput, where we've just summed all the nanoseconds per day that we get from the 16 different replicas. And so it's just a huge performance boost over what we had, what we have available in NAMD 214. And so all of that is right now available in an alpha version of NAMD 3. And now I'm showing you some very new work that is not yet available because it's not really production ready yet. But we've started to get some results now on multiple GPU performance. And so this is just showing our first attempt, that's starting to realize this, where we're trying to scale a system across multiple GPUs, in a single node, so that these are tightly connected GPUs. And so here we're seeing some really decent first results of doing that. What this approach is doing is really just employing the nickel library to first populate positions across each GPU, so that GPU can calculate its forces that it's responsible for, and then again another nickel reduction to sum the forces back. So there's a lot of overhead from this approach right now, and that's not why we're not really seeing linear scaling on this yet. But it's we feel good about the fact that this is giving us something right now. However, we haven't extended this to PME yet. PME is a little bit complicated to handle. So let's talk about that. The problem is that PME impedes scalability. So for multi-node scaling, the 3D FFT communication costs in PME grows faster than the computation cost. And so we're even seeing a problem right now for our single node multi-GPU scaling. The 3D FFTs that we wanted, that we need to do for PME for these problem sizes are too small to parallelize effectively with CUFT. Also, too much latency is introduced with an attempt to just do our own pencil decomposition and employ CUFT across 1D FFTs. So it looks like task-based parallelism here might be best as far as delegating one of the GPUs for the 3D FFTs and the reciprocal space calculation. However, doing that will require gathering all the grid data to that one GPU and then being careful not to overload that GPU with other work. So then, of course, the question is, why not use a better scaling algorithm such as MSM? So let's talk a little bit about multi-level summation method next. What this method is doing is instead of doing the calculation that PME is doing, this is splitting the 1 over R potential into not just two pieces, but we're splitting into a short range cutoff part plus these smooth parts that are successively more slowly varying, where all but the top level potential are cut off. And then these smooth potentials are interpolated from successively coarser grids. And so this the finest grid spacing H and the smallest cutoff distance A are then doubled at each successive level. So this actually gives us a linear time calculation for MSM. And so the computational steps involved calculating, again, this short range cutoff part that you can see along the bottom part of this, kind of inverted V cycle with bars across it. And then the interpolation and interpolation parts, these are really almost the same operations that you're doing when you're doing the PME charge spreading and the PME force interpolation. And then when you're at the grid levels, you have these familiar restriction and prolongation operations, just like you do with a multi-grid problem. But then the added work here is this grid cutoff calculation that you're performing. And this is simply a 3D convolution where you're convolving the charges, the grid charges with a fixed convolution kernel to get grid potentials at each of these levels. And so the reason why we haven't already been using periodic MSM is that the previous implementation was fine for non-periodic boundaries, but it was insufficient for periodic boundary conditions. It provided lower accuracy than PME, and it also required the system of atoms be neutrally charged, which is not always the case with what what the application, what people expect from the application. And so we have a very recent new development for MSM. And so this involves interpolation now with periodic B-spline basis functions, which ends up giving us the same accuracy as PME. And then we can now handle this infinite 1 over R tail as a reciprocal space calculation at the top level of the grid. And so what this allows us to do is terminate the number of grid levels long before reaching just a single point. But we can use that to bound the size of the FFT. In other words, we can make the FFT as small as what would be comfortable for just a single GPU or a single node to calculate. And otherwise, this is giving us this much better, much more scalable algorithm where the communication at each level is nearest neighbor going up the tree up to the top grid level. So this is something that we're in the process of developing right now. Now, in terms of extending NAMD3 to multiple nodes, we're interested in reintroducing Charm++ communication. And so I need to say that, you know, the way we got great performance on just a single GPU was to remove some of NAMD's infrastructure that involved the Charm++ handling of say, the force calculation out of the way. And so what we did here was we had these these GPU integration kernels call the force kernels directly. And we also had issues with just the user level threading that was going on in our sequencer objects. And so the unused sequencer user level threads are actually put to sleep, and you don't wake the threads up until you do an atom migration between patches or whenever you're doing the coordinate output. And so the question now that we're looking into is whether GPU direct messaging will be the best alternative. And we're aware that Charm++ support is now being developed to support that. So we have some additional challenges for NAMD as well. First is to have a feature complete GPU resident version. So NAMD3 for now only supports a subset of the features and not a lot of the advanced features. Another thing that poses issues for us is incorporating culvars in a way that is not going to just crush our performance. And so the way culvars is implemented and the way it talks to NAMD right now actually poses a significant performance penalty. And so we've actually considered, what if we re-implemented parts of culvars on the GPU? And finally, we are faced with the issue of introducing support for the other GPU vendors. And so we've actually been working with people from both AMD and Intel towards some initial porting of NAMD to AMD HIP and to Intel DPC++. And so that's an ongoing ongoing work for us as well. So finally, I'd like to especially acknowledge here Julio Maia, who has done the heavy lifting on the GPU developments that we have now for our single GPU and multi-GPU support in NAMD3. And of course, we get a lot of great advice from John Stone and Jim Phillips and the rest of the NAMD team. Thanks very much. Are there any questions for me?
Yes, when you're talking about GPU direct messaging, do you mean you're running a resident like GPU thread and then you call the messaging inside the GPU or actually doing it on the host?
The idea is that if we can keep data on the GPUs as much as possible without engaging the host. So whether that means things are set up by the host to go ahead and do communication of data directly between GPU on one node to another node, say.
So this is still initiated by the host, not by the GPU kernel.
So it's initiated still by the host. That was my question.
Right. Yes.
Okay.
Is it possible to initiate it from the device?
There's some work going on that, but it's a little bit tricky because you don't have the whole, communication software stack on running on the GPU.
Yeah, that's what I thought. Yeah, okay.
But
And right
but
now,
you can-
the
But you
I'm
can
s-
invent some standard. I mean, there was some effort in, for example, in MPI that they call it session. So basically, you can schedule a big message, and then every time when a piece is ready, so when the trunk is ready, and then you can say this is ready, and then MPI can send that portion of the message. So this works with GPU because then multiple threads can work on the same, different chunks, but same message, one message. So, and when each thread gets ready, it can call the function, and then MPI can trigger the send. So if you leverage this kind of API, and basically you can set up, for example, the CPU can set up the communication schedule, and then the GPU can only tell that it's ready to send. And then it's give the illusion of that the GPU is triggering the send, but actually everything is set up in the CPU, but you kind of have a quicker way of starting the communication.
I think that's fine for what we're doing, since really it's the CPU that's driving the GPU kernels to begin with. So, that
Yeah, right.
that
Various
type of control makes sense to me.
Okay.
completion and initiation is at least currently managed on the host side. So might as well. Okay.
So there's no effort basically offload everything on GPU in NAMD.
For the reasons that you just outlined, there seems to be, but every piece, I think David, correct me, but sequencer, compute, so everything to do with the data will be moved eventually to the device. That's our plan.
That's actually the goal right now. Yes.
The initiation of communication, initiation of kernels will be done by the host.
Right. Okay.
Are there any other questions? I guess we'll move to the next talk otherwise.